Entschuldigung, dass ich gerade so unterbreche. Nur wir hören schon seit einer Weile nix.
So, jetzt hören Sie mich.
Ja, jetzt können wir Sie hören. Und
Ja.
außerdem, während ich Sie gerade noch hab, wir können uns nicht über WebEx anmelden. Wir sind dafür nicht freigeschaltet. Das heißt, wir können den
Ah,
ersten Link von Ihrer Nachricht nicht folgen.
okay. Ganz vielen Dank. So, um, forgot to turn on the microphone. So if you see that, directly tell me after the first slide when I change this, but thank you for telling me now. And it's interesting that you tell me you cannot register or sign into WebEx because one of you could. Anyway, I think I will repeat very briefly for those who just joined and for those who just have the microphone now. Here the audio. So the goal of this lecture is to teach you about unsupervised learning. We talk about the scenario where you do not have labeled data. So you have the same data as before, instance features about the instances, but no labeled data. And to start with an example, we look at business consultancy firms, how they cluster markets or companies, because that's a big issue. They want to identify promising companies to buy or to sell, or markets they want to invest in. And here's one example. Imagine you have a portfolio where you are invested already. Like, let's say this is companies or markets. Then you look, what's the market share that you have already? And what's the market growth, the expected market growth in the future? So like a company that would be here would have a very high market share of a market that has expected low growth in the future. This company here has a relatively high market share in a market where the market growth is expected to be high. Let's see, I need to connect my keyboard so I can let the students in. Sure. Now, what Boston Consulting Group was doing, very simple. They just, but it made them popular. It's crazy for what you can become famous. They just divided this into 4 parts. And they said, okay, all companies that are here are considered the stars. You have already a relatively high market share, and it's expected that the market is going to grow. So that's amazing. Keep these companies if you own them already, or possibly invest in them. Here, cash cows. So it means you have a high market share, but the future expectation is relatively low, so the market is not growing a lot. So what should you do? Maybe sell them. Maybe it's a good time now to sell because there's not much growth to expect it. It's called milk the cash cow. Same about this. If you own companies or have a market where the market share is low and the growth is so low, not really attractive. That's a really simple grouping of markets or companies. It's not, but again, they became really popular with this. We want to do something a bit smarter and do this automatically, regardless of how many dimensions we have, for instance. I mean, this is simple with 2 dimensions, but how would you do this if you have 3 or 4 or 5 or even more features about your instances? So we want to have an algorithm that is grouping or clustering your instances. what would you say here? How many groups would you want to have here, and how would they be assigned? There's no right or wrong answer. Yeah. If you look at the data, so two groups like this, maybe, right? Yeah. Why would you do that? Probably because intuitively, I mean, I created this chart. So 2 is the probably obvious answer because here's like a gap. So you might think, okay, if you look at this, 1 or 2 groups would be a good answer. But it could be anything, of course. Now, it could be this, what I just showed before, but it could also be this. Or you could have 3 groups. Or even this. There's no right or wrong answer. And the question is, again, how can we come up with an algorithm that is ideally deciding all of this, but at least if we give the algorithm the number of groups we want to have, assigning the points to that. I mentioned that in the beginning already. It's very important. This is not classification we are talking about. We do not have labels. We don't know the right answer. This is clustering. There are no classes. There's no inherent right or wrong. And everything, like when I show you here these colors, I just made this up. This is what I intuitively believe might be maybe a good solution. This information is not given in the data set. And this brings us to unsupervised learning. There's some problem with my computer. Let's wait. Yeah. So the purpose of clustering is to work with the data that you have. It's not about making any predictions. And then working with the data you have and use that ideally for some business purpose. And we talk today about clustering, which is one of many application areas of unsupervised learning. You can also use unsupervised learning to reduce dimensionality. For instance, if you want to visualize your instances, then it might be useful to reduce the number of dimensions of your data. Or many of the recent developments with large language models, but also to generate images, are based on unsupervised learning. One issue here is the evaluation. We will not talk about that too much, but you can imagine that if you don't know what the right answer is, how can you say it's a good algorithm or a bad algorithm? How can you say this algorithm is better than that algorithm? It's very difficult, much more difficult than what we are talking about typically with supervised learning, where you have the right answer. Now, this is just one example of this is unsupervised learning. Maybe if you have some tool that takes 2 images as input and then creates a new image. Now, there's no right or wrong answer. You can subjectively say, oh, that's pretty good. But yeah, you cannot say that's good, that's bad. Or people may disagree. Yeah, I showed you this in the first lecture. I told you to watch that at home. So let's talk about this one example of unsupervised learning, and that is clustering. I mentioned as an example, I mentioned already customer segmentation for newsletters, something like this, but also to generate recommendations. Oh, sorry. So I showed you already one potential solution, but I guess you have now a rough idea what the goal is of clustering. But how would that exactly look like? What would be the output of the algorithm? How can you program something at a high level, just the idea? What options are there? Thinking of what you know already, like KNN or linear regression. If you want to, how could a model look here that is creating two groups? You just thought maybe, yeah? This would be one, if you somehow came up in this example with a line like this, and you could say everything here is group 1, everything left or below to the line is group 2. That would be good, right? That would be one possible solution. But that's not what we are going to look at. So do you have any other ideas? And do you have an idea why this is maybe not the best idea? Think about this for a moment. That's again, later in real life, if you work in a company, you will be facing problems like this. As a computer scientist, you must think, how can you model this simply? And in the second step, how do you exactly do it? But let's think about broadly first. How could you come up with a model, like a line? What would the alternative be? Yeah. You're one step too far. Don't think about how to do that, but what alternatives are there instead of having a line? Something like this, is that an option? Could you somehow relatively easily, do you believe it would be possible to somehow come up with a solution like this, that you have some geometric shape that tells you this is group 1, this is group 2? Yeah. Yeah, so this would be quite difficult, right? How could you, first of all, how could you save a geometric shape like this? How could you define that? I mean, literally like this shape, yeah, with all these curves. And then how could you check if a point is in this shape later? No, it's not a question for you. I tell you, this would be difficult. It would be relatively complex. Yeah? Yeah. Yeah. First of all, the student just mentioned maybe some circle and then some way of k-nearest neighbors. There's many different solutions to this. Huh? But there's problems and advantages. With a circle, one big problem is either you maybe don't have all points in there or you have overlapping circles. So difficult. So I'm showing to you one solution. It's actually probably the most simple solution. Maybe not the very most intuitive, because also no one came up with you, but do you remember what a centroid is? I mean, I don't know, maybe you didn't learn about that, but if you had that at high school geometry, maybe you did learn about that. You remember? So it's about geometry. No? Okay, I also didn't learn that at high school. Yeah, I don't know the German word, actually. So, okay, we don't need to do that if you don't know what a centroid is. I'm just telling you. A centroid is the average positions of all the points of an object. So it's kind of the average point of an object, informally speaking. So if you have this point, this point, this point, this, take their coordinates and build the average, you are getting this point. I believe it would be like the point actually where the shape would be balanced, but that's not important. So one possible solution to automatically cluster your data is to use centroids. So we want to find, actually we have to define how many clusters we want to have or how many centroids. One centroid defines not really the center, but like one centroid just defines the centroid of the cluster. We want to find clusters or centroids so that the distance for each point to its nearest centroid is the lowest. And once we have the optimal centroids, these centroids define the clusters. And then let's say we have a new point. I mean, I just said we do not want to predict. We do not want to make predictions for new unseen data. So it's not really about when a new point comes, it's about assigning points to the centroids. But let's say we come up with these two centroids somehow. Then we could say that for a given point, this distance is larger than this distance. So that means this point belongs to this centroid or to this cluster. And you can see already that I chose this example so that basically the distance here from all these points to this centroid is close, and the distance from all these points to this centroid is close. So we come up with two clusters in the same way as we intuitively thought in the beginning. It's important that these light lines, they don't exist. Yeah. If I speak of a cluster, that's a hypothetical, imaginative idea in your brain in this concept. It's not stored anywhere. It's not existent. What exists are the centroids, just 2 points. And that's a very nice thing. If you want to have 2 groups, you just need to save 2 points in the space. That requires like no storage at all. And also then later calculating the distance is relatively quick and easy to do compared to if you somehow wanted to came up and save maybe really this geometric shape here. That would take more storage, and calculating if a point is in that geometric shape would also be more complex typically than just calculating the distance. So we focus only on the centroids here. And the 2 questions are then, once you have this general idea, how many centroids and clusters? I gave you the answers already. We have to define that. K, again, is a hyperparameter. So same as in K nearest neighbors. There's no way of saying that's the perfect K in K and N, and K nearest neighbors. You can kind of try out different Ks and then say, okay, that is pretty good. Here you more or less have to just define, you must define how many customer groups do you want to have, for instance. And then the big important question, how to find the right position of the centroids. What's the best position? Make that a bit more formal. Given a data set D without a label and M data points, you want the number of K clusters, or you want the optimal set C of K centroids C. So there's C1, C2, CL, and CK. And the algorithm, again, very simple. I hope you see that all the algorithms we cover are pretty simple. You can implement them in a few lines of code. Linear regressions is a few lines of codes. KNN is a few lines of codes. Here, K-means clustering is a few lines of code. So what you do is you choose K, you initialize the K centroids randomly, and then you repeat until convergence. You remember convergence means that a certain stopping criteria is met, so the error doesn't change anymore, or you define a certain time, something like this. So what you do until convergence is you assign each point in your data set to its nearest cluster, and then you update the centroids so that they become better. What that means, we talk about in 1 minute. So I show you how this works. You randomly initialize, so you define that you decide K equals 2. And then you randomly initialize your clusters, your centroids. So that, let's say randomly one centroid is here, one centroid is here. And then for each data point, you calculate the distance, identify the centroid with the lowest distance, and identify the corresponding cluster. Okay, how to calculate the distance, we had that already, so we can skip that. And now how the update works is that the new centroid, the updated centroid, is just the new the centroid of the assigned points. So you have your data points, you randomly initialize the centroids, you assign your given points to the centroids, and then you take all the points that belong to centroid 1 and calculate the new centroid of those points. You take all the points that belong to centroid 2 and calculate the new centroids of those points. And that's it. So I just drew this by hand, yeah, so it's not perfect, but let's assume, just going back here, if that's your random starting position, so actually it's not really correct. I think, I'm not sure if this distance here is really larger than this distance, but I just made this by gut feeling and I said this point belongs here. Now, if you take the centroid of this point, this point, this point, this point, and this point, then it would be roughly, again, I just drew this by hand, roughly here. If you take the centroid of this point, this, and this, the new centroid would be, I think it would not be here, it probably would be rather here, but anyway, that's not the point. And then you calculate again for each point what's the nearest centroid. So before this point, the nearest centroid was this one, but now the nearest centroid is this. So it becomes orange. So you have the two new centroids and you have the two new clusters. Again, probably this should be green, but for the sake of illustration, I assume that this distance is lower than this distance. And then you do it just again. So you take the centroids, move them, set the new centroids, and then at some point, the centroids will not change anymore. And then you are done. Yeah? Very good question. Does that mean there's only one optimal solution? And including like kind of, is it deterministic and is there always, or should there always be the same optimal outcome? What do you think? First of all, is there always the same outcome? Would there be local minima or local optima? And do you always have the same outcome? Not always the same. What do you think? First of all, is it deterministic? Do you always end up with the same clusters, the same centroids? Just your gut feeling. Who thinks you will always end up with the same clusters? Raise your hands. Don't be shy. You are not on the video. Nobody sees if you do it wrong. Who thinks you may end up with different clusters each time? Okay. That's the correct answer. We talk about that a little bit later. So it's not, you do not always end up with the same clusters, and there is some relatively small risk of ending up with a local optima, like something you really don't want, but very likely you end up with a good solution. Just again, what I said, convergence after a given amount of iterations, if you have very limited computing power, typically you stop when your centroids don't change anymore, or actually when the assignment of the points to the centroids don't change anymore. Now, I mentioned already it's difficult to evaluate this, but how can you measure how good the clustering worked? You are scientists, so you want numbers, so you are quantitative people. How can you quantify somehow, just going back here, how good this is? Yeah. Yeah, you could, as a simple metric, just calculate the distance from each point to its centroid and sum up all the distances. And if you were to have two different algorithms, or if you just run this multiple times, you would take that algorithm or solution that gives you the lowest total distance. So could you ever have let's call it an error? Could you ever have an error of 0? In which case would you maybe have an error of 0? Yeah. You mean points, right? Data points. Exactly. When you would have as many, and you're not changing the data points, if you have as many clusters or centroids as data points, because then each data point would have like its own centroid and cluster, and then the distance would be zero. But that, of course, is not what you want. I mean, then you don't need clustering if each data point is its own cluster. So normally you never have a perfect solution. You never have a distance or an error of 0. Yeah, so that is the overall, it's called within cluster sum of squares. It's again squared typically to, actually I don't know why it's squared in this case, because, oh yeah, so that the distance is not negative. Could the distance ever be negative? Well, I'm not sure, but anyway, so you take the distance between a given point. Yeah, it could be negative. This expression here could be negative. So you take the coordinates of one point or the distance between these points and possibly square it. No, the distance could not be negative. Anyway, and then you sum that up for all the clusters. Yeah. Yeah. We do not make predictions. It's not the goal to make a prediction for a new instance. The goal is really only to look at your existing data and say, this is my customers. These customers belong to group 1. These customers belong to group 2. Exactly, it's grouping. That's the, yeah, yes, exactly. No, it's not for making predictions. It's quite different from everything we have talked about so far. You can kind of forget everything we've talked about so far. Yeah. Yeah, exactly. It's you could kind of consider this like a decision matrix, and that you, yeah. So if you came up with this solution, it would be good enough, right? It would, or actually, if you compare this solution and this solution, it would lead to the same outcome. It would lead to having these 3 points being assigned to this centroid and these 3 points being assigned to this centroid. Still, with the previous formula, this would be considered a better solution. But it really doesn't matter because, again, it's not about predictions or anything. So the outcome would be the same here. So in theory, but of course, you also don't know that beforehand. You could stop already here. Anyway. Yeah, we had this question already. Like we said, the lowest error would be achieved if you have, if k would equal m. M is the number of instances in your data set. There's one rule of thumb, one method how you can determine a good k, but it's not really hard science. It's more a rule of thumb. So it's called the elbow method. What this shows is, ignore this for now. Look at this data set A. These are actually your data points. And if you cluster them, this shows the number of clusters. And this is the sum of the squared errors. So if you have one cluster, you will always get a chart similar to this. The more clusters you have, the lower the error becomes. And then at some point, it becomes 0. So the question is here, which one to use? And you cannot build a derivative or something like this and say that is the best. The elbow method tells you just that where the slope becomes suddenly less steep, you would choose that. So you see here, high slope, and then here you see something like an elbow. If you hold your arm like this, or like this, this is the optimal K, and the elbow would be here. So it would be probably a good idea to choose K equals 3. But it's not always like this. It can also look like this. And where's the elbow here? Maybe here, maybe here. Well, probably not here, but probably here or here. So it's difficult to say. And then again, it depends on your application. Maybe you want many groups. Maybe you want 10 customer groups and not 2 or 3. Then you just choose 10. What is a good clustering outcome? How can you like roughly define that? If you visualize it in a low-dimensional space, you could argue the outcome is good if the clusters are well separated, like in the example that you can have like a line between them. That would be actually then linearly separable, this one. But at least they are grouped in one direction and another direction. If you have relatively simple shapes of clusters, and it's not relevant for k-means clustering, but Some clustering algorithms could also generate overlapping clusters, similar to circles, and you typically don't want to have many overlaps of the clusters. What are the disadvantages of k-means? If you think of this, what's maybe not ideal? Yeah. Yeah, that's a good point. Yeah, outliers. K-means is sensitive to outliers. Something else? No? Yeah, you don't know what k is. And it would be nice sometimes to have maybe probabilities. So it's hard clustering. A point belongs either to this cluster or to that cluster. And let's say you have your two centroids here and you have one point almost in the middle. Sometimes it would maybe be good to be able to say, well, this cluster could belong like an overlapping, like to both clusters. You don't have that with k-means. I want to show you a few visualizations just to show you how this develops. So in this example, I think you have 1, 2, 3, 4. You have 4 centroids, k equals 4. Let's see. And then you see all the different iterations. Can I make this? And you also see that each time this starts, you end up with different solutions. So that's the first run, second run. Do you see it? Yeah. Okay, I don't know why that YouTube is really slow all the time here. Yeah. Anyway, it's all the, yeah, it's just the same. Good. We do an example now to really make you understand how this works. Just to make it, so this is a rather unusual way of writing it. Here I wrote the instances here and the features here. This can also happen in the exam, just to make you not being too fixed on that the instances are here normally and the features are here. Camera off. So let's assume we have 4 instances, each instance defined by 2 features, x1 and x2. You see the visualization here, instance 1, instance 2, instance 3, and instance 4. In the first iteration, we randomly choose some centroids. So centroid 1 has the coordinates 0.5 and 1. That's here. And centroid 2 randomly got the coordinates 2 and 3.5. That's here. Centroid 2, coordinates 2 and 3.5. Good. I think, yeah, you don't need to do that now. I just show you this actually. Yeah, maybe you do it. We have 3 minutes. Calculate this distance between centroid 1 and instance 1. Okay. Gives me time to drink my coffee. Okay. Does this work? Can you try? Go to menti.com, type in this code. Okay, many of you chose 1.5. I also have this, none of it. Who did the mistake? You or me? But okay, so those who calculated 1.5, what did you calculate? Did you do a mistake or did I do a mistake? Yeah. No? Yeah, so like this. Good. Check this at home. If it's 1.5 or 1.12, but I'm at least one other student has the same like me, so that, yeah. Okay, so he forgot to square the 0.5. Anyway, double check this at home to be really sure, but you got the basic idea. So in the first step, you calculate the distances from all points to all centroids, because you don't know in the beginning which centroid is closest. Yeah, so you calculate here centroid 1, centroid 1, centroid 1, centroid 1 to instance 4, 3, 2, and 1. And then here for the second centroid and the 4 instances, you calculate the distance. Then you look for each instance, what's the distance to the 2 centroids, which one is smallest, and you assign the point to the corresponding centroid. Just for here, instance 2. The distance between instance 2 and centroid 1 is 2.5. The distance between instance 2 and centroid 2 is 0.5. So 0.5 is smaller than 2.5. So instance 2 belongs to centroid 2. Once you did that, you update your data. So actually, let me see. Yeah, these were your first centroids, and then this is the new centroids. And you see that centroid 1 now is actually identical to instance 1. You also see that here. And then the second centroid is here. And then you just continue. Now you calculate the distances between all the centroids and all the points, identify the clusters, have the new centroids. So now the centroid moved, I think it was here before, it moved to here. Here, I think it was before like here, and now it moved to there. And the third iteration, and I believe then, yeah, then you are done. That is really the optimal solution in this made up example. But will k-means always find an optimal solution? We mentioned this already. The answer is no. Could you think of a really simple example where k-means does not come up with an optimal solution? Where you just have 1, 2, 3, 4 data points and 2 clusters. So an example, 4 data points, 2 clusters. And that if you start accidentally at a very special random solution, you would end up with something that is probably not how it should be. Four data points, two centroids. I'll show you something. That's an example of a local minima. If you, for some, so the blue ones are your data points, 1, 2, 3, 4. And if for some reason you would end up, or actually randomly start with centroids like this, then you would have a grouping, a clustering like that. And very, very likely, again, there's no proof that this is not good, because there's no right or wrong answer. But I mean, if you just look at it, this is probably not what you would want to have. You would want to have that this is one cluster and this is one cluster. Yeah, this is what you would want to have. And in most cases, you would also achieve if you just randomly start a little bit different. Any questions so far? Yeah. Okay, the student said maybe a solution to this problem would be to only start with one centroid randomly, and then say the second centroid would be somewhere else with a certain distance. Maybe. I mean, this is really the most simple clustering algorithm. It's like decades old. There are much more advanced algorithms. There's lots of work to improve this. I don't know exactly how to avoid this, but I'm very sure there is ideas, and maybe what you just said. I don't know, maybe it works. So that was your first unsupervised learning algorithm, and that already concludes today's lecture, but I am finished for today, but you are not. So there's a recorded lecture on decision trees and ensembles, which is in OneDrive already. So I ask you to watch this now or later or tomorrow, but there will also be a lab session about this topic. It's a recording from last year from my PhD student. He always gave this lecture. He and also I don't have more time today. So that's it. Any more questions? Yeah. Anyone else tried the OneDrive link I just sent yesterday evening? Does it work? Yeah. So it works for them. So for you? It doesn't work. Okay, let me double check. I'm stopping the recording.